The sound was wrong. That's what Howard Finch noticed first. Not the hydraulic whine of the test rig, not the steady hum of the factory floor behind him, but the crack. Sharp. Final. Like a rifle shot echoing through the Willys Overland plant in Toledo, Ohio, December 17, 1942. A brand new MB Jeep sat mounted on the test stand, its rear axle connected to hydraulic rams designed to simulate the worst conditions a military vehicle could face. They'd run this test dozens of times. Standard procedure: load the axle progressively, record the stress points, verify it meets Army specifications. 2,100 pounds of cargo capacity should be routine, except the axle housing just cracked at 1,850 pounds. Finch hit the emergency stop, stared at the fractured steel like it had personally betrayed him. This wasn't supposed to happen. These axles had passed inspection. The steel came from Republic Steel, one of the most trusted suppliers in the country. Heat treatment followed every specification in the Army's technical manual. Yet here it was. Failed below its rated capacity, he ordered another test. Same result at 1,920 pounds. Then another failure at 1,880. By the end of the day, they destroyed 6 axles. Not one reached the 2,100-pound threshold the military required. This wasn't just embarrassing, it was dangerous. The War Department had already ordered 361,000 Jeeps. Thousands were already in North Africa supporting Operation Torch. Field reports were starting to trickle back about axle failures on rough terrain, but everyone had assumed it was abuse. Poor maintenance. Now the engineers in Toledo were staring at a fundamental materials problem. The steel itself couldn't handle the job. What made this terrifying was the timing. American forces were fully committed in 2 theaters. The Jeep had become the backbone of military logistics, more critical than anyone had imagined during its rushed development in 1940. These vehicles hauled ammunition, towed artillery, carried wounded soldiers, dragged supply trailers across bombed-out roads from Casablanca to Guadalcanal. An axle failure in combat didn't just mean a broken vehicle. It meant stranded troops, lost supplies, and potentially lost lives. The metallurgical analysis came back 3 days later. The carbon steel used in the axle housings had adequate tensile strength on paper, around 80,000 pounds per square inch. But under the combination of torsional stress, impact loading, and repetitive flexing that Jeeps experienced off-road, the crystalline structure of the steel was developing microfractures. Tiny cracks propagating until catastrophic failure occurred. The steel wasn't bad, it just wasn't good enough for what the military was asking it to do. By Christmas 1942, Willys engineers were in crisis meetings with Army Ordnance Department representatives. They needed a solution. Fast production couldn't stop. The invasion of Europe was already being planned, and it would require tens of thousands more Jeeps. Strengthening the axle by making it thicker would add weight and cost, reducing vehicle performance. Using more expensive steel alloys was an option, but the War Production Board had strict allocation rules. Premium steel was reserved for aircraft, naval vessels, heavy armor. Someone suggested they contact Russell Moll. The problem with standard carbon steel in 1942 wasn't immediately obvious to anyone outside the metallurgy world. On a molecular level, steel is iron atoms arranged in a crystalline lattice with carbon atoms wedged between them. The carbon makes iron harder and stronger, which is why a steel axle can handle loads that would bend pure iron like a pretzel. Standard axle steel used by Willys contained roughly 0.40% carbon by weight. That gave it 80,000 psi tensile strength. For a stationary beam or building frame, perfectly adequate. But an axle doesn't just sit there bearing weight. It twists every time a Jeep's wheel hits a rock or drops into a rut. The axle experiences torsional stress. The housing tries to twist in one direction, while the differential gears inside resist, creating shearing force through the steel. At the same time, the weight of the vehicle and cargo creates bending stress. Now add thermal cycling, the axle heating up during operation and cooling down at rest, which causes metal to expand and contract. the crystalline structure of plane. Carbon steel simply couldn't handle this combination of stresses repeatedly without developing what metallurgists call fatigue, cracks. Here's what was happening at the microscopic level. Steel crystals, called grains, have boundaries where the atomic structure changes orientation. These grain boundaries are the weakest points in the material. Under repetitive stress, tiny voids would form at these boundaries. Each time the axle twisted or flexed, these voids would grow slightly. After thousands of cycles, basically a few hundred miles of driving on rough terrain, the voids would connect into actual cracks. Once a crack started, it would propagate rapidly through the steel until the entire housing failed. The Army's metallurgists understood this phenomenon. They called it fatigue failure, and it had been a known problem in rotating machinery since the 1800s when railroad axles started breaking. The standard solution was to specify a safety factor, basically overbuilding the component so it could handle more stress than it would theoretically encounter. The Jeep's axle had been designed with a safety factor of about 1.5, meaning it should handle 50% more than the rated load, but battlefield conditions were exceeding even that margin. Part of the issue was how Jeeps were actually being used versus how they'd been designed. The original specification called for a quarter-ton truck, 500 pounds of cargo, plus 4 soldiers. In practice, combat units were loading them with ammunition cases, jerry cans of fuel, water containers, extra weapons, and whatever else needed moving. A fully loaded combat Jeep often weighed over 5,000 pounds total. Nearly double the design weight, the axles were living on borrowed time. The heat treatment process made things worse in some cases. To achieve required hardness, steel axle housings were heated to around 1,550 degrees Fahrenheit, then quenched in oil to rapidly cool them. This process, called hardening, creates a very hard but brittle surface. The housings were then tempered by reheating to about 800 degrees to reduce brittleness. But if temperature wasn't precisely controlled, you'd end up with steel that was either too brittle and would crack easily, or too soft and would deform under load. Quality control varied between suppliers and even between batches from the same supplier. Republic Steel and the other suppliers weren't doing anything wrong. They were following the specifications they'd been given. The problem was those specifications were based on peacetime engineering assumptions. Nobody had anticipated that these vehicles would be subjected to the kind of sustained abuse they were experiencing in North Africa's desert terrain or the Pacific's jungle trails. The steel formula. That worked fine for farm trucks and civilian. Vehicles simply couldn't cut it in combat. Russell Moll wasn't the kind of metallurgist the War Department typically consulted. He ran a small independent laboratory in Bethlehem, Pennsylvania, about 90 miles north of Philadelphia. His reputation among the big steel companies ranged from eccentric genius to stubborn crank, depending on who you asked. Moll had graduated from Lehigh University in 1923 with a degree in metallurgical engineering, right when the American steel industry was booming. Instead of joining one of the major corporations like U.S. Steel or Bethlehem Steel, he'd set up his own consulting practice, working with smaller manufacturers who needed custom alloy solutions. What made Moll different was his approach to steel formulation. Most metallurgists in the 30s and early 40s worked within established guidelines. The American Iron and Steel Institute published standard compositions for various grades of steel, and engineers selected from these standards based on their application. It was efficient, predictable. Moll thought it was lazy. He believed every application had an optimal alloy composition, and finding it required experimentation rather than just picking from a catalog. This philosophy had earned him 23 patents by 1940, covering everything from corrosion-resistant alloys for chemical plants to specialized tool steels for precision machining. The Army had actually approached Moll once before, in early 1941, about a year before the Axle crisis. They'd asked him to develop a lighter steel formula for helmet shells. Moll spent 3 months creating an alloy that was 18% lighter than standard manganese steel helmets while maintaining the same ballistic protection. He demonstrated it with live fire tests, submitted his findings, waited for a contract. The Ordnance Department rejected it. Their reasoning was straightforward. Switching to a new alloy would require retooling multiple factories, retraining quality control staff, rewriting technical manuals. With war looming and production ramping up, they couldn't afford the disruption. They went with the heavier standard steel. Moll had been furious, not because of the lost contract, but because he knew soldiers would be carrying extra weight that didn't need to be there. He'd written a detailed letter to the War Department explaining that battlefield mobility could be the difference between life and death, that a few months of retooling would pay dividends for years. The letter was filed away and forgotten. After Pearl Harbor, Moll had offered his services again, volunteering to work on any materials problems the military was facing. He'd received a polite thank you note and nothing else. The big steel companies had the contracts, and the government saw no reason to bring in an outsider. But Howard Finch at Willys remembered Moll's name. Back in 1938, Finch had worked for a small Pennsylvania manufacturing company that made industrial pumps. They'd been having problems with impeller shafts corroding in caustic chemical environments. Standard stainless steel lasted about 6 months before failing. Finch's boss had hired Moll, who developed a custom chromium-nickel alloy with molybdenum additions that lasted over 3 years in the same conditions. The solution had saved the company thousands of dollars in downtime and replacement costs. When the Jeep axle failures started piling up in December 1942, Finch picked up the phone. Moll listened to the problem, asked a few questions about loading conditions and failure modes, said he could have a prototype formula ready for testing in 3 weeks. He didn't ask about contracts or payment terms. He just said that if American soldiers were dying because of failed axles, he wanted to fix it. Finch sent him a failed axle housing and detailed stress analysis data on December 21st. Moll received it on December 23rd and went straight to work in his laboratory, canceling his Christmas plans. Moll's laboratory notebooks from late December 1942 show a man obsessed with a single question. How do you make steel that can twist, bend, and absorb shock repeatedly without developing fatigue cracks? The answer wasn't going to be found in simply increasing carbon content. Too much carbon would make the steel harder, but more brittle. Exactly the opposite of what was needed. The axle housing needed to be both strong and tough, a combination that requires careful alloying. Moll focused on 2 elements that most manufacturers were using sparingly: chromium and molybdenum. Chromium had been added to steel since the 1860s, primarily to improve corrosion resistance and hardness. In concentrations above 11%, it creates what we call stainless steel. But Moll wasn't interested in stainless properties. He wanted the structural benefits that chromium provided at lower concentrations, around 1 to 2%. At these levels, chromium does something crucial. It refines the grain structure of the steel. Remember those grain boundaries where fatigue cracks start? Chromium promotes the formation of smaller, more uniform grains during heat treatment. Smaller grains mean more grain boundaries per unit volume, which paradoxically makes the steel stronger because cracks have to navigate a more complex path. Molybdenum was the more exotic addition. In 1942, the United States produced only about 40 million pounds of molybdenum per year, and most of it went to high-speed tool steels and armor plate. Molybdenum is expensive and difficult to work with, which is why it appeared in very few standard steel formulations. But Moll knew its properties intimately from his previous work. Molybdenum dramatically improves a property called hardenability, which is how deeply hardening penetrates into a thick piece of steel during heat treatment. More importantly for the axle application, molybdenum increases the steel's resistance to temper embrittlement, a phenomenon where steel becomes brittle after being held at certain temperatures. Moll's formula called for 1.4% chromium and 0.35% molybdenum in a steel base with 0.38% carbon, 0.75% manganese, and trace amounts of silicon. On paper, this doesn't sound revolutionary, but the magic was in how these elements worked together. The chromium refined the grain structure. The molybdenum ensured that structure remained stable through heat treatment and thermal cycling. The slightly reduced carbon content compared to standard axle steel gave the alloy more ductility, the ability to deform slightly before cracking, and the manganese helped with strength without adding brittleness. Here's where Moll violated military protocol. The War Production Board had strict allocation rules for strategic materials. Molybdenum was classified as critical, meaning its use required specific authorization. Adding it to something like Jeep axles, which were being produced by the tens of thousands, would consume molybdenum that was supposedly reserved for heavy armor and naval gun barrels. Moll didn't care about the paperwork. He had enough molybdenum in his laboratory to create test samples, and he was certain the performance gains would justify the material cost once the bureaucrats saw the results. The heat treatment process Moll developed was equally unconventional. Instead of the standard quench and temper approach, he specified a process called austempering. The steel would be heated to 1500 degrees Fahrenheit to reach the austenite phase, where the crystal structure is most receptive to alloying elements. Then, instead of quenching in oil, it would be quenched in a molten salt bath held at exactly 550 degrees. At this temperature, the steel would transform into a structure called bainite, which has properties intermediate between the very hard martensite that forms during normal quenching and the softer pearlite that forms during slow cooling. Bainitic steel is exceptionally tough and resistant to crack propagation. By January 8, 1943, Moll had produced 6 prototype axle housings using his formula and heat treatment process. He subjected them to tests in his own laboratory that simulated millions of stress cycles. Not one failed. Howard Finch received Moll's prototype axle housings on January 11, 1943, along with a 47-page technical report that detailed every aspect of the new alloy formula and heat treatment process. Finch read through the report twice, then walked it directly to the chief engineer's office. Within an hour, they'd scheduled testing for the following morning. But there was a problem. Official Army testing protocols required witnesses from the Ordnance Department, documentation in triplicate, and approval from the commanding officer at the Detroit Arsenal, which oversaw all-wheeled vehicle production. That process would take weeks, possibly months. The engineers at Willys didn't have months. They decided to run unofficial tests first. If Moll's axles failed like the standard ones, there was no point involving the Army bureaucracy. If they succeeded, well, then they'd have the data to push for official trials. On the morning of January 12th, a small group gathered around the test rig. Finch, 2 other engineers named Robert Kelly and Frank Davis, and a machinist who would operate the hydraulic rams. No cameras, no official observers, just a handful of men who wanted to know if Moll's steel could actually do what he claimed. They mounted the first Moll prototype on the rig. Standard procedure was to increase load in 200-pound increments, holding each level for 5 minutes while monitoring stress gauges. At 2,100 pounds, the Army's required capacity, the gauges showed stress levels, about 15% lower than the standard axles at the same load. Finch told the machinist to keep going. At 2,500 pounds, the axle was still holding. Stress readings were now roughly equivalent to what standard axles showed at 1,800 pounds. At 3,000 pounds, there was some deflection in the housing, but no cracking. They stopped at 3,200 pounds, not because the axle was failing, but because the test rig wasn't designed to go higher safely. They removed the prototype, inspected it under magnification, found no cracks or permanent deformation. The steel had flexed under the extreme load and returned to its original shape. Kelly, who'd been skeptical of bringing in an outside consultant, just stared at the axle housing and said something unprintable. They mounted a second prototype and ran it through a different test: cyclic loading. Instead of steady weight, they applied rapid load variations from 500 to 2,500 pounds, simulating what a Jeep would experience bouncing across rough terrain. After 50,000 cycles, equivalent to roughly 3,000 miles of hard off-road driving, the prototype showed no signs of fatigue cracking. Over the next week, they destroyed the remaining 4 prototypes through increasingly absurd tests. They loaded one to failure, which finally came at 4,800 pounds, more than twice the Army's specification. They took another and subjected it to 200,000 load cycles before it developed the first hairline crack. They heated one in a furnace and quenched it in ice water repeatedly to test thermal shock resistance. They took the last one and deliberately created a stress concentration by drilling a small hole in the housing, then loaded it until the crack propagated. Even with the artificial defect, it held to 2,900 pounds. The results were impossible to ignore. Moll's formula produced axles that could handle approximately 312% of the rated load, compared to standard steel's inconsistent performance below 100%. Fatigue life was at least 6 times longer, and perhaps most impressively, the failure mode was ductile rather than brittle. When standard axles failed, they shattered suddenly. Moll's axles deformed gradually, giving visual warning before catastrophic failure. In a combat situation, that difference could mean a driver would notice problems and get the vehicle to safety, rather than having the axle explode without warning. Finch wrote up the results and submitted them to the Detroit Arsenal on January 19, 1943. He requested authorization for official Army trials and approval to begin sourcing the chromium-molybdenum steel for production. Response came back on February 3rd. Request denied. The alloy formula was not on the approved materials list, and adding it would require review by the Materials Standards Committee, which met quarterly. The next meeting was scheduled for April. The rejection letter sat on Howard Finch's desk like a hand grenade with the pin pulled. The logic from the Detroit Arsenal was maddeningly bureaucratic. Changing a material specification in an active production contract required review at multiple levels. First, the Materials Standards Committee had to evaluate whether the new alloy met Army-wide requirements, not just for Jeeps, but potentially for any wheeled vehicle. Then, the War Production Board had to approve the allocation of chromium and molybdenum, which meant analyzing how those materials would be diverted from other programs. Finally, all existing suppliers would need to be notified and given the opportunity to bid on producing the new steel, which meant Republic Steel, Inland Steel, and 3 other companies would need time to evaluate their capacity. The estimated timeline was 6 to 9 months. By then, another 150,000 Jeeps would roll off production lines with axles that couldn't handle battlefield conditions. Finch tried appealing directly to Colonel James Lawson, the Ordnance Department officer responsible for wheeled vehicle procurement. Lawson was sympathetic, but constrained by the same regulations. He couldn't unilaterally approve a materials change without the committee's blessing. More critically, he had budget concerns. Chromium-molybdenum steel cost approximately 23% more per pound than standard carbon steel, across hundreds of thousands of axles that translated to millions of dollars in additional costs. Congress had authorized specific amounts for vehicle production, and exceeding those budgets required justification to the War Department. What made this particularly frustrating was that field reports kept confirming the problem. In February 1943, a maintenance depot in Oran, Algeria, catalogued 247 Jeeps with failed or cracked axles out of roughly 3,000 vehicles that had been in North Africa for 4 months. That's an 8% failure rate in a relatively short deployment period. Mechanics in Oran were cannibalizing parts from the worst vehicles to keep others running, but they were losing ground. Similar reports came from the Pacific Theater, where Jeeps operating in New Guinea and Guadalcanal were experiencing axle failures on jungle trails that were barely more than mud paths. Behind the scenes, a different battle was brewing. Republic Steel learned about Moll's formula through industry contacts and was deeply unhappy. They'd invested heavily in expanding their carbon steel production capacity to meet military contracts, building new furnaces, hiring thousands of workers. If the army switched to a specialized alloy that required different production processes, Republic would need to retool significantly or potentially lose contracts to competitors who could produce the chromium-molybdenum steel more efficiently. In March 1943, Republic's executives met with War Production Board officials and argued that the current axle failures were due to abuse and poor maintenance, not materials deficiency. They had some support for this position. A February inspection of damaged Jeeps in North Africa found that many units weren't following maintenance schedules in the technical manuals. Axle oil was being changed infrequently or not at all. Vehicles were being overloaded far beyond their specifications. Some units were even using Jeeps to tow loads they were never designed to handle, like artillery pieces that exceeded the vehicle's towing capacity. Republic Steel's argument was that better training and maintenance discipline would solve the problem without expensive materials. Changes. The counter-argument came from an unexpected source. Lieutenant Colonel William Goad was a field maintenance officer attached to the 1st Armored Division in Tunisia. He'd been a mechanical engineer at Ford Motor Company before the war and understood both vehicles and military logistics. Goad compiled a detailed analysis showing that even Jeeps that received perfect maintenance according to Army standards were failing at unacceptable rates. He documented cases where axles failed on vehicles with less than 2,000 miles on the odometer, properly maintained, operating within their rated capacity. His report, filed in March 1943, concluded that the steel itself was inadequate for the mission requirements. Goad's report landed on desks in Washington just as planning for the invasion of Sicily was intensifying. The operation would require thousands of Jeeps, and the chiefs of staff were already worried about logistics in the Mediterranean theater. Nobody wanted to hear that a fundamental component was failing. The Materials Standards Committee suddenly found time to meet in early April, several weeks ahead of their scheduled quarterly meeting. They invited Russell Moll to present his findings. By July 1943, the situation in North Africa had evolved from an engineering concern into a strategic crisis. The Allied victory in Tunisia in May had required massive logistics efforts, and the Jeep fleet had performed worse than anyone anticipated. Maintenance records from the Sioux Corps showed that axle-related breakdowns had sidelined approximately 11% of all Jeeps during critical phases of the campaign. That might sound like a small percentage until you consider what it meant in practice. Supply convoys delayed, ammunition not reaching artillery units on schedule, wounded soldiers waiting longer for evacuation, reconnaissance patrols unable to reach their objectives. General George Patton was not a patient man under the best circumstances, and these were far from the best circumstances. Patton had taken command of the 2nd Corps in March 1943 after the disaster at Kasserine Pass, and he'd driven his logistics officers mercilessly to improve supply line efficiency. When he learned that broken axles were contributing to delays, he dictated a message to the War Department that was characteristically blunt. The relevant portion, now declassified, read, "I don't give a damn what your procurement regulations say. My vehicles are failing, and it's not because my men are abusing them. Fix the problem, or I'll have my ordnance people weld railroad rails to the axles if that's what it takes." Patton's intervention had weight because, by July, he was preparing for Operation Husky, the invasion of Sicily scheduled for early August. The operation required 1,600 Jeeps just for the initial landing forces, with thousands more to follow as the campaign progressed. Sicily's terrain would be even more demanding than North Africa. Mountain roads barely wide enough for a single vehicle. Grades that would test every component. If the axle problem wasn't solved, Patton made it clear he'd hold someone personally responsible when the operation inevitably suffered logistics failures. Field reports from Tunisia told a consistent story. Jeeps hauling supplies through the mountains near Kasserine experienced axle failures at rates 3 times higher than vehicles operating on relatively flat coastal roads. The issue wasn't just weight. It was the combination of weight and constant torque reversals from climbing and descending steep grades. A Jeep going up a 15-degree slope with a full load put enormous stress on the rear axle. Coming down the same slope, even with the driver using engine braking, created different but equally severe stress patterns. After dozens of these cycles, the standard steel axles were accumulating fatigue damage at an alarming rate. Lieutenant Colonel Goad had by this point become an unofficial evangelist for Moll's alloy formula. He'd managed to get 3 Jeeps fitted with the prototype axles, though officially they were still unauthorized for field use. Goad assigned these vehicles to the roughest duty he could find, hauling ammunition to forward artillery positions in mountainous terrain. Over 3 months of operations, these 3 Jeeps accumulated more than 8,000 miles, each under conditions that had destroyed standard axles in under 3,000 miles. Not one of the Moll axles failed. Goad documented everything meticulously. Photographs of the routes, weight measurements of the loads, maintenance logs showing the vehicles received no special treatment. In late June, Goad's commanding officer, Major General Ernest Harmon, forwarded the documentation directly to General Dwight Eisenhower's headquarters in Algiers. Eisenhower's chief logistics officer, Brigadier General Leroy Lutz, read through the report and immediately understood the implications. The Army was about to launch the largest amphibious operation since Gallipoli, and a known materials deficiency was going to compromise. Logistics Lutz sent a priority cable to the War Department on July 8, 1943 request: immediate authorization for chromium-molybdenum. Axle steel per attached specifications. Field testing confirms 3-fold improvement in durability. Sicily operation success may depend on logistics reliability. That cable changed everything. When combat commanders and theater logistics officers are saying an operation's success is at risk, procurement regulations suddenly become negotiable. On July 15th, the War Department issued an emergency authorization for Willys Overland to begin producing Jeep axles using Moll's formula. The authorization came with conditions. It was classified as a field modification rather than a standard specification change, which meant it bypassed some of the normal approval processes. Republic Steel and other suppliers were not required to retool. Instead, a smaller specialty steel company in Pennsylvania, Midvale Steel, received a contract to produce the chromium-molybdenum axle housings, exclusively for new Jeeps being shipped to the Mediterranean theater. The emergency authorization should have been the end of the story. It turned out to be just the beginning of a different kind of battle. Midvale Steel began ramping up production of Moll's chromium-molybdenum axle housings in early August 1943, with the first production units scheduled to ship to Willys assembly plants by September. The initial contract called for 15,000 axle housings, enough to equip Jeeps heading to the Mediterranean and Pacific theaters. Russell Moll provided detailed technical specifications and even spent 2 weeks at Midvale's plant in Pennsylvania, training their metallurgists on the ostempering heat treatment process. On September 3rd, the first production batch of 500 axle housings arrived at the Willys plant in Toledo. Quality control inspectors immediately noticed something wrong. The housings had a slightly different surface appearance than the prototypes, a mottled pattern that suggested inconsistent heat treatment. Destructive testing of sample units showed strength values approximately 40% lower than Moll's prototypes. They weren't as bad as the old carbon steel axles, but they weren't anywhere close to the performance that had justified the emergency authorization. Howard Finch called Midvale's plant manager, who insisted they'd followed Moll's specifications exactly. Moll drove to the Midvale plant the next day and requested access to their raw materials and production records. What he found was disturbing. The molybdenum content in the steel was testing at 0.9%, instead of the specified 0.35%. That difference might seem tiny, but in metallurgy, precise composition is everything. Molybdenum was the key element that enabled the deep hardening and temper resistance that made Moll's formula work. At half the required concentration, the steel would still be better than standard carbon steel, but it wouldn't deliver the dramatic performance improvement that field tests had demonstrated. Midvale's purchasing records showed they'd ordered molybdenum from their usual supplier, Climax Molybdenum Company in Colorado. The shipment manifests indicated the correct grade and quantity, but spectrographic analysis of the molybdenum actually used in production showed it was contaminated with excessive amounts of iron and silicon, which reduced its effectiveness. Either Climax had shipped substandard material, or something had happened to the molybdenum between Colorado and Pennsylvania. Moll requested samples be sent to an independent laboratory for verification. While waiting for those results, a second problem emerged. In late September, Midvale reported that their salt bath equipment for the austempering process kept experiencing temperature control failures. The molten salt bath needed to maintain 550 degrees Fahrenheit with minimal variation. Midvale's equipment was fluctuating between 520 and 580 degrees, which meant some axle housings were being heat-treated incorrectly. When Moll inspected the equipment, he found that someone had modified the thermocouple calibration settings. The modifications appeared deliberate, not the result of normal wear or drift. The picture that emerged over October 1943 was increasingly suspicious. Midvale's plant manager was replaced suddenly, officially due to health reasons. The independent laboratory analysis came back, showing the molybdenum shipment was indeed contaminated. But Climax Molybdenum insisted they'd sent pure material and suggested contamination occurred during storage or handling at Midvale. The FBI was quietly brought in to investigate possible sabotage, given that this involved war production. Their investigation, declassified decades later, found evidence of at least 2 instances of deliberate tampering, but couldn't conclusively identify the perpetrators. The most likely explanation, though never proven, was industrial sabotage motivated by economic competition. Republic Steel and the other major suppliers stood to lose significant contracts if Moll's formula became standard across all military vehicle production. The chromium-molybdenum steel required specialized production capabilities that favored smaller companies like Midvale, who were more agile in retooling. Several Republic Steel executives had close relationships with Midvale employees through industry associations. The FBI investigation noted these connections, but found no direct evidence of coordination. What saved the program was Russell Moll's stubbornness and the Army's desperate need. Moll essentially moved into Midvale's plant for 6 weeks, personally overseeing every aspect of production. He arranged for molybdenum to be shipped directly from Climax to Midvale under guard. He recalibrated the heat treatment equipment himself and installed tamper evidence seals on the control systems. He implemented a testing protocol where every single axle housing was inspected before shipping, not just random samples. Production efficiency dropped significantly, but quality improved to match the prototype specifications. By November 1943, reliable chromium-molybdenum axle housings were finally flowing to Willys assembly plants. The first Jeeps, equipped with production versions of Moll's axles, shipped to Italy in December, where Allied forces were grinding their way up the Italian peninsula through some of the most difficult terrain of the war. June 6, 1944. The beaches of Normandy were chaos incarnate. 5,000 ships had delivered 156,000 Allied troops to 5 landing zones along 50 miles of French coastline. Among the massive inventory of equipment coming, ashore were 2,400 jeeps designated for everything from reconnaissance to ammunition hauling to communications relay. The invasion planners had learned hard lessons from North Africa, Sicily, and Italy. Logistics could win or lose a campaign, and the Jeep had proven to be the workhorse that made rapid mobile warfare possible, but only if the vehicles could actually handle the demands being placed on them. The Normandy terrain presented challenges that combined the worst elements of previous campaigns. The Norman bocage country consisted of small fields surrounded by thick hedgerows on raised earthen banks, creating a landscape that channeled vehicles onto narrow lanes and farm roads. These roads, designed for horses and carts, were barely wide enough for military vehicles. Heavy rains in early June had turned many routes into mud channels. Jeeps were hauling supplies forward through this terrain, often towing trailers loaded with ammunition that pushed the vehicles to their absolute limits. Within the first week of the invasion, maintenance units on the beaches were seeing the difference between old specification and new specification axles. Jeeps equipped with the standard carbon steel axles were arriving at repair depots with cracked housings at roughly the same rates that had plagued operations in Tunisia, but the Jeeps with Moll's chromium-molybdenum axles were holding up remarkably well. Maintenance report from the 7th Corps dated June 14, 1944, noted that among 312 Jeeps examined after the first week of operations, only 3 equipped with the new axles showed any stress cracks compared to 41 with standard axles. The real test came during the breakout from the Normandy beachhead in late July. Operation Cobra, the offensive that finally broke through German lines and allowed Allied forces to sweep across France, required unprecedented logistic support. The advancing armored columns were consuming fuel and ammunition at rates that strained the supply system to its breaking point. Jeeps formed the backbone of what became known as the Red Ball Express, a dedicated truck convoy system that ran 24 hours a day, hauling supplies from the beaches to the front lines. By August 1944, some of these supply jeeps were covering 300 miles per day on roads that ranged from decent French highways to hastily repaired bomb-damaged routes to barely passable dirt tracks. They were hauling loads that often exceeded their rated capacity, towing trailers full of jerry cans, operating with minimal maintenance because stopping for repairs meant breaking the supply chain. The Jeeps with standard axles were failing at catastrophic rates. A logistics analysis from August 1944 estimated that axle failures were taking approximately 400 Jeeps per week out of service across the European theater. The Jeeps with Moll's axles told a different story. They weren't indestructible. Nothing could withstand the kind of sustained abuse the Red Ball Express involved, but they were surviving at dramatically higher rates. A detailed study conducted by Army Ordnance officers in September 1944 tracked 500 Jeeps through 30 days of continuous Red Ball operations. The 250 Jeeps with standard axles experienced 87 axle failures, and the 250 with chromium-molybdenum axles experienced 11 failures. That's an 8-fold improvement in reliability under the most demanding conditions. The Army had yet encountered those numbers translated directly into military effectiveness. Every Jeep that didn't break down was one more vehicle delivering ammunition to artillery units, fuel to tank columns, rations to infantry divisions. The ability to maintain higher operational readiness rates meant that advancing units had the supplies they needed when they needed them. Logistics officers began specifically requesting Jeeps with the upgraded axles for critical supply missions, though officially there was still no designation that distinguished them from standard vehicles. By the fall of 1944, word had spread through maintenance units across all theaters. Mechanics could identify the chromium-molybdenum axles by small markings Midvale had started adding during production. These Jeeps became prized assets. Unit commanders would try to hold onto them rather than releasing them to motor pools. Maintenance crews would preferentially repair them rather than cannibalize parts for other vehicles. An informal black market even developed where supply officers would trade other equipment for Jeeps known to have the upgraded axles. The combat effectiveness of Moll's formula was now beyond dispute. The Army had the field data to prove that his alloy was saving vehicles, enabling logistics, and ultimately saving lives. Yet officially, The chromium-molybdenum steel still wasn't the standard specification. It remained a field modification authorized only for specific production runs. The bureaucratic machinery that had resisted changing the formula in 1943 was still in place. When the war ended in August 1945, the US military had produced approximately 640,000 Jeeps. Of those, only about 85,000 had been equipped with Russell-Moll's chromium-molybdenum axles. The rest still used the standard carbon steel that had proven inadequate years earlier. This wasn't because the Army didn't know Moll's formula was superior. Every field report, every maintenance analysis, every logistics study confirmed the dramatic improvement in durability and reliability. The reason was more complicated and in many ways more troubling. Institutional inertia, combined with economic interests that valued stability over innovation. In the immediate post-war period, the military began the enormous task of demobilizing and converting from wartime to peacetime operations. Hundreds of thousands of Jeeps were declared surplus and sold to civilian buyers. Farmers, construction companies, anyone who wanted a rugged utility vehicle. These surplus Jeeps became foundational to the recreation vehicle market and helped establish Jeep as a civilian brand. But the Jeeps being sold had the old axles, and new civilian Jeeps being produced by Willys Overland for the commercial market also used standard carbon steel. Specifications. Russell-Moll expected that his formula would become the new standard for all Jeep production and potentially spread to other civilian vehicles. After all, why would anyone voluntarily use inferior steel once a better alternative had been proven? He contacted Willys in late 1945 about licensing his metallurgical patents for civilian production. The company's response was polite but firm. The chromium-molybdenum formula was more expensive to produce, and civilian customers weren't willing to pay the premium. The military had covered the additional cost because lives were at stake. Civilian buyers just wanted the cheapest functional vehicle. What Moll didn't fully understand was that the automotive industry in the 40s operated on extremely thin profit margins. A 23% increase in axle steel costs translated to about an 8% increase in total vehicle price. For a civilian Jeep selling for roughly $1,200, that meant an extra $96. In a competitive market where Ford and Chevrolet were also producing utility vehicles, that price difference could determine whether customers bought a Jeep or a competitor's truck. Willys calculated that the improved durability wouldn't be valued enough by civilian buyers to justify the higher price. The military's position was even stranger. Despite all the field evidence supporting Moll's formula, the Army Ordnance Department never officially changed the material specification for Jeep axles. When new military contracts were issued in the late 40s and early 50s, they still called for standard carbon steel meeting the original 1940s specifications. The chromium-molybdenum axles were allowed as an acceptable alternative, but they weren't required. This meant contractors could bid lower prices using the cheaper steel and still meet the contract terms. Part of this decision was driven by peacetime budget constraints. Congress had slashed military spending dramatically after 1945, and the armed forces were under constant pressure to reduce costs. Procurement officers were rewarded for getting lower prices, not for specifying higher quality. Materials that cost more. The institutional memory of wartime logistics failures was fading quickly as the white officers who'd fought those battles retired or moved to other assignments. The new generation of peacetime procurement staff looked at spreadsheets, not field maintenance reports from Normandy. But there was another factor, one that only became clear decades later through declassified documents and industry histories. The major steel companies had significant political influence in Washington. Republic Steel, U.S. Steel, and Bethlehem Steel employed thousands of workers in politically important states like Pennsylvania, Ohio, and Illinois. These companies had invested heavily in carbon steel production capacity during the war and wanted to protect that investment in peacetime. Adopting specialized alloys for automotive production would have required retooling and potentially shifted contracts to smaller companies like Midvale that had the specialized capabilities. Industry lobbying worked quietly through trade associations and congressional relationships to ensure that military specifications remained flexible enough to allow standard carbon steel. This wasn't dramatic or conspiratorial, just the normal operation of economic interests protecting themselves. The steel industry argued, not entirely incorrectly, that maintaining production flexibility and competitive bidding would result in lower costs for taxpayers. What they didn't mention was that those lower costs came with reduced durability and higher maintenance expenses over the vehicle's lifetime. Russell Moll watched his innovation get buried under economic and bureaucratic calculations. His patents were valid, and he continued to license them for specialized industrial applications where performance justified the cost. But the mass-market breakthrough he'd expected never came. The automotive industry continued using standard carbon steel for axles and drive components through the 50s and 60s, gradually improving through incremental refinements rather than adopting the dramatic step change Moll had demonstrated. The story of Russell Moll's chromium-molybdenum formula didn't end with its post-war suppression. It went underground, quietly influencing military and industrial metallurgy in ways that weren't publicly acknowledged for decades. The engineers and metallurgists who'd worked with Moll steel during the war carried that bouquet of knowledge into their post-war careers. When the military began developing new vehicles in the 50s and 60s, these men were in positions to influence material specifications, and they remembered what had worked in combat. The M151 Jeep, which replaced the World War II Jeep in 1960, used a chromium-molybdenum alloy for its rear axle shafts. The specification wasn't identical to Moll's formula. The chromium content was slightly lower, and the heat treatment process was different. But the fundamental principle was the same, using chromium and molybdenum together to create steel that could handle high stress and fatigue loading. The official procurement documents didn't cite Moll's work or acknowledge the World War II field experience. The specification was presented as a new development based on contemporary metallurgical research, but anyone familiar with the history could see the connection. The same pattern appeared in other military vehicle programs. When the Army developed the M35 cargo truck in the 50s, the drive axles used a chromium-molybdenum steel alloy. The M113 armored personnel carrier introduced in 1960 used similar steel for its final drive components. By the 70s, chromium-molybdenum alloys were standard in military vehicle drivetrains. Though the formulas varied by application and manufacturer, Moll's specific composition wasn't universally adopted, but his insight that this combination of alloying elements solved the fatigue and torsional stress problems had become accepted engineering wisdom. The civilian automotive industry took longer to catch up, but economic pressures eventually forced changes. As vehicles became heavier and more powerful through the 60s and 70s, standard carbon steel axles and drive shafts increasingly became the weak point. Performance vehicles especially pushed the limits of component strength. The muscle car era saw numerous driveline failures as engines, producing 400 horsepower, tried to transmit power through axles designed for half that output. Manufacturers began selectively upgrading to alloy steels for high-performance applications. By the 80s, chromium-molybdenum steel had become common in heavy-duty truck applications and four-wheel drive vehicles. The cost premium that had seemed prohibitive in 1945 had shrunk as production volumes increased and manufacturing processes improved. When companies like AM General developed the HMMWV, the military vehicle that replaced the M151 in the 80s, chromium-molybdenum steel was specified from the beginning for all driveline components. The vehicle was designed to handle 2,500 pounds of cargo and frequently operated at much higher loads in combat zones. The engineers knew from historical experience that standard steel wouldn't survive. Russell Moll's influence extended beyond Earth. When NASA began developing the Mars rovers in the 90s, the engineering teams faced a unique challenge: creating wheels and axles that could handle Martian terrain for years without maintenance or replacement. The rovers would experience constant stress cycling as they climbed over rocks and navigated crater slopes, exactly the kind of fatigue loading that destroys standard steel. The solution: NASA's metallurgists developed, used titanium alloys rather than steel, but the design philosophy came directly from Moll's work. Select materials that maintain toughness and fatigue resistance under cyclic loading. The Spirit and Opportunity rovers, which landed on Mars in 2004, used wheel axles made from a titanium alloy that contained chromium and molybdenum, among other elements. Opportunity operated for almost 15 years, traveling over 28 miles across Martian terrain that would have destroyed any Earth vehicle using standard materials. When engineers analyzed the rover's wheel performance through images sent back from Mars, they noted minimal stress cracking in the axle components, despite millions of stress cycles. The design principles Moll had proven in a Pennsylvania laboratory in 1943 were now enabling planetary exploration. 140 million miles from Earth modern metallurgy textbooks discuss chromium-molybdenum steels as a standard alloy family, designated as 4130, 4140, and other numbers in the ASI classification system. These alloys are used in aircraft landing gear, oil drilling equipment, high-performance bicycle frames, and countless other applications where strength and fatigue resistance matter. Most engineers using these materials don't know the name Russell Moll or the story of how his alloy proved itself on the beaches of Normandy. The knowledge has been absorbed into the collective understanding of how to design components that won't fail under stress. Moll himself lived until 1979, working as a metallurgical consultant almost until his death at age 78. He held 68 patents by the end of his career, covering everything from corrosion-resistant alloys to specialized heat treatment processes. He never received public recognition for his World War II contributions. There were no medals, no ceremonies, no mention in the official histories of military logistics. He was fine with that. In an interview late in his life, Moll said he'd done the work because American soldiers needed better equipment, not because he wanted recognition. The fact that his principles were being used everywhere, even if his name wasn't attached, was satisfaction enough. But maybe that's not the full story. Maybe there's something else worth considering about what happened to Russell Moll's steel, about why innovation gets buried, about why better solutions don't always win. The sound that Howard Finch heard on December 17, 1942, that crack like a rifle shot, was the sound of something breaking. Not just an axle, but the assumption that what we've always done is good enough, that the manual contains all the answers. That expertise means following established procedures rather than questioning them. Moll proved that a small laboratory with limited resources could solve a problem that billion-dollar corporations and government agencies couldn't. Not because he was smarter than everyone else, but because he was willing to ignore what everyone knew was true and test whether it actually was. The chromium-molybdenum formula worked. Field testing proved it worked. Combat operations confirmed it worked. Lives were saved because it worked. And yet for decades, the people making decisions chose the cheaper, inferior option because changing specifications was inconvenient. Because protecting existing contracts mattered more than performance. Because institutional inertia is easier than institutional change. That's the real story. Not the metallurgy, not the technical specifications, but the choice between what works and what's easy. Every Jeep that made it through the hedgerows of Normandy with Moll's axles intact was a small victory for that choice. Every vehicle that failed with standard steel was a reminder that sometimes knowing better isn't enough. You have to fight for better. The engineers at Willys knew better by January 1943. The field commanders knew better by summer. The logistics officers knew better by D-Day. And still, the system resisted change until economic interests and bureaucratic momentum could be carefully managed, until the innovation could be slowly absorbed without disrupting the comfortable arrangements that benefited the people in charge. Russell Moll died in 1979, 34 years after the war ended. His obituary in the local paper mentioned his patents and his consulting work. It didn't mention that his steel helped win World War II, because officially, it didn't. Officially, it was just a field modification, an alternative specification, one option among many. But the mechanics who kept those Jeeps running knew. The drivers who pushed them through mud and mountains knew. The logistics officers who calculated how many vehicles would break down on which roads knew. They knew that sometimes one person, working in a small laboratory in Pennsylvania, can change the outcome of a war, not through heroism or sacrifice, but through stubborn insistence that there has to be a better way, and the willingness to prove it. The crack that echoed through the Willys plant in December 1942 was the sound of failure, but it was also the sound of opportunity. The chance to question, to test, to improve. Most of the time, that sound gets ignored, covered up, explained away as acceptable losses or operational realities or budget constraints. Russell Moll heard it and went to work. That's the lesson. Not the chemistry, not the heat treatment process, not even the 8-fold improvement in reliability. The lesson is that the system will always resist change, even when change saves lives. That innovation threatens comfortable arrangements. That better solutions get buried under economic calculations and procurement regulations and institutional inertia. And that sometimes, one stubborn metallurgist with a small laboratory can prove that everything we know is wrong. The steel didn't win the war, but it helped. And maybe that's enough. Maybe that's all anyone can do. Find one problem, solve it, prove it works, and let the people who come after decide whether they want to use it or bury it. Russell Moll solved his problem. The rest was up to everyone else. And in the end, slowly, quietly, without recognition or ceremony, his solution became the standard. Not because bureaucracies changed their minds, but because the people who knew better kept using it, kept specifying it, kept remembering what worked when everything else failed. The institutional memory that faded in Washington survived in maintenance depots and engineering offices and university laboratories. The innovation that got buried officially lived on unofficially until eventually, decades later, it wasn't controversial anymore. It was just how you made steel that could handle stress. That crack in December 1942 echoed for 40 years before it finally stopped. Before Moll's formula became so standard that nobody questioned it anymore. Before the innovation became conventional wisdom. Maybe that's how real change happens. Not through dramatic moments or official recognition, but through the slow, stubborn insistence of people who know better that eventually, given enough time, the truth wins. Or maybe it's simpler than that. Maybe it's just that good steel lasts longer than bad bureaucracy. And in the end, the axles that didn't break outlasted the regulations that tried to stop them.